Jai Hind to all. Now, my name is Divya Sharma. Now, today's video lecture is on wave propagation. So, this is the introduction. When electromagnetic waves carrying information is generated by the transmitting antenna, it propagates towards a receiving antenna after undergoing some different phenomena. It may be wired, it may be wireless, or wireless, it may be radio waves like that. An electromagnetic wave transmitted by the antenna in a transverse wave. A transverse wave is also known as traveling wave. A transverse wave is a wave which occurs with direction perpendicular to the direction of propagation. Now, what are the types of electromagnetic waves? So, there are three types of electromagnetic waves: ground wave, or you can say surface wave, space wave, and the third one is sky waves. So, first, what do you mean by ground waves or sky or surface wave? A part of the wave traveling along or near the surface of the earth, that is known as ground wave. And some waves travel directly to the receiving antenna, that is known as space wave. Some waves travels upward toward the sky and get reflected back to the receiving antenna, that is known as sky waves. So, these are the three types of electromagnetic waves. Now, modes of propagation. So, the method by which electromagnetic waves travel in free space is known as mode of propagation. So, mode of propagation may be ground wave propagation, space wave propagation, and sky wave propagation. Now, first is plane earth reflection. Now, when your wave is traveling from transmitter to receiver, so it may travel or it may travel by a direct wave or direct path, or it may be indirect path. So, direct path means what? Let it be, this is your transmitting antenna, this is your receiving antenna, and your wave is traveling directly from this transmitting antenna to receiving antenna. So, that is known as direct wave. Now, when your wave when you are sending wave from transmitting antenna to receiving antenna, and it may, you have another medium, let it be this is medium 2, or you can say this is your earth. So, your wave is traveling from this point to this, means you have to travel your wave from this point to this wave. First is direct wave and second wave is indirect wave, means it is reflected from this point and then it will reach at the receiving antenna. So, this is known as reflected wave, or you can say here this is ground reflected wave or surface wave. So, this is, and this one point is also you should remember, the wave propagation can be obtained by means of space wave propagation when transmitting and receiving antenna are elevated. This propagation is known as line of sight propagation, and the reason, this is the reason that two antennas are within the sight of the vision. Now, this is also, these are the three points you should remember when you are considering the case of plane earth reflection. The transmitted and receiving waves will have the same amplitude, and the earth is considered to the perfect conductor having infinite connectivity. And the second point is that if the surface of the earth is smooth and has finite conductivity, then the amplitude and phase of the reflected wave will differ from that of the incident wave. And the third point is, when the surface of the earth is rough, then reflected wave will be scattered and their amplitude will be reduced as compared to the amplitude of the smooth surface. So, these are the 3 points you should remember, you should consider when you are considering the case of plane earth reflection. Now, the roughness of the surface is represented by capital R, and it is generally estimated by the Rayleigh criteria. Its formula is R is equal to 4 pi sigma sin theta upon lambda. Now, what do you mean by sigma? Sigma is standard deviation of the surface, and sin theta, so theta is angle of the incident on Earth's surface and lambda is the wavelength. So, this is the relation in between R and sigma, theta and lambda. So, R is equal to 4 pi sigma sin theta upon lambda. So, this is the roughness of the surface. If the surface is smooth, then value of R is less than 0.1. If R is greater than 10, then surface you can say that is rough. When the angle of incidence is approximately equal to the grazing angle, theta tends to 0, the reflection coefficient approaches to -1 irrespective of the wave polarization. Now, let us consider a medium of finite conductivity, your conductivity is represented by sigma and the dielectric constant. So Maxwell equation, you all know Maxwell equations are, first this is the Maxwell equation, del cross H is equal to epsilon into del E upon del T plus sigma E. So this is the Maxwell equation for a medium. Now time varying electric field is given by E is equal to E naught e की power j omega t. Now if we differentiate, let us consider this is equation 1, this is equation 2. So differentiating this equation, del E upon del T means if you are differentiating this E with respect to T, then you will get here E0 j omega e की power j omega t. Now here you will get E j E. Now E is what? 1 upon j omega del E upon del T. Now put the value of E from this equation in equation first, Maxwell equation. So you will get here del cross H is equal to epsilon del E upon del T plus, here put the value here, E is equal to what? 1 upon j omega del E upon del T. When you will put here E, value of E, then you will get here del cross H is equal to epsilon del E upon del T plus sigma upon j omega del E upon del T. Now you can take common del E upon del T from these two terms. You will get here epsilon plus sigma upon j omega bracket close. Now del E upon del T, and del cross E is equal to what? Let it be, this is epsilon dot, and epsilon dot into del E upon del T. So this is your del cross H. Now where epsilon naught is equal, epsilon naught is epsilon dash is equal to epsilon plus sigma upon j omega. It is considered in the previous equation that this is equal to what? This is epsilon dash, right? Now here, so the value of dielectric constant is complex in nature and it is given by epsilon dash is equal to epsilon, you can take common in bracket 1 plus sigma upon j omega epsilon. So we shall consider the reflection coefficient following two cases. First is reflection coefficient for the horizontal polarization and the second for the reflection coefficient for the vertical polarization. Now space wave or transpose wave communication. Now sky cannot propagate above frequency of 30 megahertz and the frequencies above 30 megahertz are known as space wave propagation. Now ground waves die near the transmitting antenna. The electromagnetic waves that propagate from transmitter to receiver in Earth troposphere, that is known as space wave, or you can say direct wave propagation. The troposphere region is within 15 km above the surface of the Earth. Space wave also known as direct wave, or they travel directly from transmitter to receiver. So this is the structure of space wave propagation. You can see this is your Earth. Let us consider this is your transmitting antenna. This is your receiving antenna. You are transmitting signal from transmitter to receiver. So this is the way how we are sending your signal from transmitter to receiver. This is, you can see, this is the distance of 15 km. This is the distance of 50 km. So here your troposphere is present. Here this is your ionosphere, right? So this whole process is known as space wave propagation. It means you can see here there is a line of sight distance because you can see the transmitter and receiver directly, right? So for space wave, two antennas must see each other, that is there must be line of sight path between them. Space wave propagation is, you can see here in this structure, because you are, this is your transmitter, this is your receiver, and you can directly see your transmitter signal from this receiver. Means you can your signal is traveling directly from transmitter to receiver, and you can see this from transmitter side, you can see the receiver signal, receiver point. So this is line of sight. Now multi-path space wave propagation. Here this is your transmitting antenna, this is your receiving antenna. Now here you are sending your wave from transmitter to receiver. So transmitter height is HT and receiver height is HR. So when you are sending your signal from transmitter to receiver, so there are two ways or multiple ways, but here we are considering first way is we are sending your signal from transmitter to receiver directly, and here your signal is goes to the Earth, then it will reflect back to the receiver side. So this is your reflected ray. So you can say this is multi-path space wave propagation. Now space wave propagation. In practice, the signal received at the receiving antenna is not just due to the direct wave coming from the transmitter receiver, but it will reflect it to the ground and then it will reflect back to the receiving antenna. So these are the two ways you can see your signal is traveling from transmitter to receiver, by the direct path or by the indirect path. Now here you can see this is your optical horizon. Now this is transmitter side, this is your receiver side, and this is your HT, means this is your earth, this is the height of the transmitter HT, this is the height of the receiver HR. Now here this O is the origin point, R, this is the R, means this is the radius of this transmitter to from this origin, and from this origin to this receiver. So it is represented by capital R. Capital R means actual radius of the earth. Now here you are sending your signal from transmitter to receiver. So you can see you are sending your signal through radio waves. So this is the way, and when you are sending your signal by optical horizon, so this is the way. Now max radio range or optical range or of line of sight. So line of sight, it means this is your transmitter, this is your receiver, you are sending your signal from transmitter to receiver. So this is your line of sight, because you can see the receiver point from the transmitter, and from the transmitter side you can see the this is the receiver point. So you can see from the receiver point, you can see the transmitting point. So this is your line of sight. Now here you can draw, this is your origin, this is your transmitter, this is your receiver. So height of the transmitter is HT and receiver height is HR. This is your O point origin. Now you are sending here perpendicular to this ABC point, and this is R, radius of this figure. This is also same, this is also same. It means what? It means your wave is traveling from transmitter to receiver with this radius. You are considering here origin to this transmitter, your radius R, and from this point midpoint B, that is also R, same, and this is also same. Now here you can see, if you are traveling from this distance to this distance, this is D1, you are considering this is D2, and whole is the distance that is representing by D. So the optical range of the propagation can be calculated by using the heights of the transmitting and receiving antennas as shown in figure this. Although the waves follow curved path, but to simplify the mathematics, the path are taken to be straight. Now you are what you are doing here, you are taking mathematically. So you have to consider straight path. Let this is D1, this is D2, and this is whole D, complete D, and this is the curved surface from transmitter to receiver. Now you have to do here calculations for this line of sight. D is the distance between transmitter and receiver. HT is the height of the transmitting antenna from the ground. HR is the height of the receiving antenna from the ground. R is the actual radius of earth, that is 6370 km. Now you can see in the figure, this D is the distance from, this is transmitter, this is receiver, this is your earth. So height of this transmitter to earth, that is HT. Height of this receiver point from this earth, that is HR. Distance from transmitter to receiver is represented by D. Now here this is the radius which is covering by radius denoted by R, from transmitter to this origin and receiver to this origin. Now optical range of line of sight, it means what? D is equal to D1 plus D2. Now if you will calculate from triangles ABO and CBO, so ABO and CBO, you are considering these two triangles, and you can find out here D1 is equal to under root H1 plus R square minus R square, that is equal to what? HT plus R ka whole square minus R square. So HT square plus R square plus 2 HT R minus R square. Now here you can see D1 is equal to what? D1 is equal to under root 2 HT R. Why it is so? Because HT square is less than 2 HT R. Now similarly you can find out for D2. D2 is equal to what? Under root HR plus R ka whole square minus R square. So that is equal to what? Under root 2HR into R. It means what? HR square is less than 2HR. So you will get here d1 is equal to what? Under root 2 htr, and d2 is equal to under root 2 hrr, right? Now d max, so d max you can find out is equal to what? d1 plus d2. So add this d1 and this d2, so that is equal to d max. D max is equal to, you can take common under root 2r, and in under root you will in bracket you will get here under root ht plus under root hr, that is d max. So it is, its units are in meter. Now radius of the earth, that is equal to what? 6370 kilometer. Now you can put here the value of r, that is equal to 6370 kilometer. So d max is equal to under root 2 into 6370 kilometer. So kilometer you can convert it in meter, 10 to the power 3 in bracket under root ht plus under root hr meter. Now here you can calculate this under root value, and you will get here 3.57 in bracket under root ht plus under root hr, that is you are calculating here in kilometer. So d max is equal to what? D max is nearly equal to 4 in bracket under root ht plus hr under root hr kilometers. So this is your d max for this line of sight. Let us take an example. Calculate the maximum radio horizon, means in range, for a transmitting antenna of height 2 to 5 meter and a receiving antenna of 1 meter height. What is the new maximum radio horizon if the height of the receiving antenna can be raised up to 16 meter above the ground surface? So ht is equal to 2 to 5 meter, hr is equal to 1 meter. Now d max you can find out, that is equal to what? 4 under root ht plus under root hr. So here put the value of ht, here put the value of hr. So you will get here 64 kilometer. Now ht is equal to 2 to 5 meter, hr is equal to 16 meter here. So d max is equal to 4 under root 2 to 5 plus under root 16. So this is your d max when you have ht is equal to 2 to 5 meter and hr is equal to 16 meter. So your d max is equal to 76 kilometer. Now next example, find out the radio horizon distance of transmitting antenna 70 meter high, receiving antenna 45 meter high, maximum communication distance between two antennas. Now find out here d1 and d2 and d max. So d1 is equal to what? Under root 2r ht. So you all know r is equal to what? 6370 kilometers. So put here the value in meter. So 6370 into 10 to the power 3. So you will get here in kilometer 29.86 kilometer. Now according to that, you can similarly you can find out d2 is equal to what? Under root 2r hr. So put here the value of r, that is equal to 6370 kilometers. So put here this value, and hr is equal to what? hr is 45 given here in this question, and here in the first part also here 70 is given in the question, transmitting antenna. So you can find out d2 is equal to what? 23.94 meter, right? And d1 is equal to 29.86 kilometer. Now you can convert this is also in kilometer. This is in not in meter, this is in kilometer. Yes, this is in kilometer, because here 23.94 into 10 to the power 3 meters. So convert it in kilometer, you will get here 23.94. This is kilometer, right? Now d max is equal to what? d1 plus d2. So d1 is equal to what? 29.86 kilometer and d2 is equal to 23.94 kilometer. So d max is equal to 53.8 kilometer. So this is the way how you can find out radio horizon distance of transmitting antenna, receiving antenna, and the maximum communication between these two antennas, transmitting and receiving antenna. Now surface wave or ground wave propagation. So this is the classification of surface wave propagation is propagation of radio waves. This is your ground wave, sky wave, and ground wave is also classified into two types, surface wave and space wave. Now space wave is also classified into ground wave, ground reflected wave and direct wave. So this is the classification of propagation of radio waves. Now here surface wave or ground wave propagation. Now you can see this is the vertical polarized wave. Here these are your magnetic fields and these are your electric fields. Now these waves are guided along the surface of the earth. This type of propagation takes place when transmitting an electric field receiving antenna are close to the surface of the earth and supported its lower edge by the presence of the ground. And the second point is the propagation is used at lower frequency. Lower frequencies are up to 2 megahertz. So the ground wave is produced by the vertical antennas, and that is known as vertically polarized. The horizontally polarized antennas are not preferred because the horizontal component of the electric field in touch with the earth in short circuit by the earth. So you can see this is the structure of this vertical polarized wave. So you can see this is ground wave or surface wave propagation. This is your transmitter, this is your receiver. So distance between transmitter and receiver is represented by D. If you are considering the origin of this distance, that is D, and complete distance from transmitter to receiver is represented by capital D. Now tilting of ground waves. Tilting of ground waves means the ground wave is attenuated at its propagate due to the imperfect nature of the earth. The attenuation depends upon frequencies or surface irregularities, permittivity and conductivity of earth. At higher frequencies, the attenuation by ground is more than at the lower frequency over the same ground. Besides ground attenuation, there are another attenuation like diffraction, tilt in the wave front as the wave progresses over the curvature of the earth. So the wave front starts gradually tilting more and more. You can see, let it be, this is your transmitter, this is your receiver. So your waves, when you are sending your wave from transmitter to receiver, so it will tilt like this angle of theta 1, here theta 2, here theta 3, here theta 4. So these are the successive wave fronts, or you can see this is the direction of propagation, means you are sending your signal from transmitter to receiver. So, and this is the surface of the earth. Your angles are theta 1, theta 2, theta 3, theta 4. So theta 4 is greater than theta 3 and theta 3 is greater than theta 2 and theta 2 is greater than theta 1. It means what? It is showing the tilting of the wave front. So it is important to mention here that maximum range depends on not only on the frequency but also on the power. Hence the range can be increased by increasing the power of the transmitter. Now free space propagation, or you can say fundamental equation for free space propagation, that is equal to what? PR is equal to PT upon 4 pi R square. Here you are considering transmitting antenna be radiating uniformly in all directions. So here this is the transmitting antenna and your transmitting antenna radiates uniformly in all directions. So receiving antenna at point P, you can see here this is your receiving antenna at point P, and radius from this transmitter to receiver is represented by capital R. So the power density at point P due to the transmitted power this point to the transmitted power P, so that is equal to what? PR is equal to PT upon 4 pi R square Weber per meter square. And PR is what? PR is your isotropic antenna power density, and this is equal to the ratio of the power per unit area of the wavefront. Now GT is what? GT be the maximum directivity gain of the transmitting antenna. Now GT is equal to what? Test antenna power density upon isotropic antenna power density, and test antenna power density is represented by P test and isotropic antenna power density is representing by PR. So GT is equal to what? P test upon, means test antenna upon PR, and P test antenna is equal to what? PR into GT. And you can here put the value of PR from the previous equation, that is equal to PT upon 4 pi R square into GT. Now the receiving antenna will capture only a portion of this radiated power. If the effective capture power of the receiving antenna is AR, then the received power, that is equal to what? P test is equal to PT GT upon 4 pi R square into AR. This AR is what? AR is the effective aperture. And AR is equal to what? Lambda square upon 4 pi into GR, and GR is what? Maximum directional gain of receiving antenna. Here you can substitute from equation 4th in third, means from the previous equation you can put the value and you can find out AR, you know, lambda square upon 4 pi GR. So you can put here AR value in the equation P test, that is equal to what? PT GT GR lambda square upon 4 pi ka R square. So this is what? This is your Friis formula for wave propagation. And if you want to find out from here, if you want to find out maximum range from this equation, so r square max is equal to pt gt gr lambda square upon 4 pi r square p test. So from this equation you can find out r max. So that's all for today, and next video lecture we will cover in the next lecture. Thank you.